I am going to go through some stuff for 8b. We're going to use second derivatives for the first time today. By the way, hello again. What we've done before is found second derivatives. Now we are going to use them. So I've drawn a few graphs for you here. You can see that the red graph is y equals x squared, and you can see that there's only one turning point. We obviously know this. You can see also the black graph here is y equals x cubed, and you can see that there are two turning points. And you should also know that x to the power of 4 is going to have three turning points, right? That's like a little W shape. 1, 2, 3. Okay, so the thing that you need to remember is that every power has one less than that turning point, right? So 4, 3 turning points, 3, 2 turning points, 2, 1 turning point. This is because of derivatives. When we derive this, the highest power is now 1, and we're finding information about turning points. When the highest power is 3, we've got two pieces of information. There will be two x solutions because we're going to go backwards to something that looks like this, which gives us two x solutions, which gives us two turning points, and so on and so on and so on. So I'm going to get rid of that, but I just wanted to remind you that that's how that information is connected. So let's have a look at the red one here. When we derive this equation, we solve for x, which tells us about the single turning point that we have. And obviously looking at this, we know that this is a minimum turning point. It is the minimum point of the graph. When we go over to the green one, we have a negative. This is the maximum turning point of the graph. So what I want you to do is we're going to do this algebraically, but it's really helpful if you can picture these graphs and understand whether they're minimums or maximums without having to do the work. So if you need to prove it, then you still need to do it. But there is a little mini shortcut where if you know what the graph looks like, then you can tell whether it's going to be a maximum or a minimum. And same with the black one here. If you know that this is a positive cubic, you should know the shape of it. The first turning point is going to be a maximum, and the second turning point is going to be a minimum. We did a little bit of this last year, but only with predictability. So if I have y equals negative x cubed, it's going to do that, which means that the first turning point is now a minimum and the second turning point is now a maximum. So if we can predict the shape of the graph, we can double check our work and also maybe skip a couple of steps occasionally. So let's have a go at doing some of this. Oh, actually, before I do that, let me just remind you that there is also a third version where it sort of does this. This is a type of cubic where this is called a point of inflection. Uh, how do I spell that? My brain has just stopped working. This is a point of... Nope, I'm on the wrong page. There it is, inflection. For some reason, I could not remember if it was inflection, which it's not. Of course, this is flex. Oh my gosh, I am so tired. All right. And now I've actually erased the actual graph. Oh, why is it doing that? That's really annoying. Okay, you get my point. If I do this, so what this means is this is a stationary point. That's why we don't always call them turning points, because these ones, oh, you can't see my cursor again. The red, green, and black graphs are all turning points, but this brownish graph that I've drawn down the bottom is still a cubic, but what it does is it pauses, and then at the point of inflection, the derivative or the gradient is 0, and then it continues up in a positive direction. You can also do it the other way around. This is still a point of inflection, but the gradient is always negative in this one. So the gradient is negative here, apart from the point of inflection where it's 0, and in this one, the gradient is always positive. So there is a slight difference. And what we need to do is be able to recognize that from particular equations. So let's actually do that. There are two different methods in which you can do this, and I'm going to teach you one because I think the other one is not actually that useful. Uh, and the second one is just using second derivatives, which is the whole point of it. So let's do that. So if I have, let's start with this, y equals x squared plus 9 all over x. So the first thing I'm going to do is rewrite this to be x squared plus 9 put some brackets around it, and then this is x to the power of -1. Now, the first thing I'm going to do is expand my brackets, right? There's no power here, so I'm allowed to do that. So I'm going to multiply. So I know we write it like this, but just a reminder, it's the same as writing it like this. So sometimes people forget that you can just expand your brackets. But again, it's only true because the power here is only 1. If it was anything else, you couldn't. So I'm going to multiply these two things. Remember, you add the powers. So this just becomes x because -1 plus 2 is 1. And then I have plus 9x to the power of -1. So what I need to do now is say at this point, well, so sorry, I need to derive it first, right? So at this point, the derivative is 0. Okay, anyway, so let's do dy dx. So at the derivative, let's subtract 1 from this. So this is just 1. Obviously, this turns into 1. 1 times 1 is 1, and -1 is 0. You can't even see what I'm doing. This is so annoying. Just a reminder that what we're really doing is this is a 1. So 1 times 1 is 1. And then this is x to the power of 0, which is just 1. So this turns into 1. Then this becomes -9 because the power of -1 multiplies that, which becomes -2. So now I've got 1 minus 9 over x squared. So now what I'm saying is that at the stationary point, whoops, let's move that up. At the stationary point, the gradient is 0. So let's work out what we're doing here. So I'm going to bring, well, actually, let's bring the second part across because then I don't have to deal with any negatives. All right, so then I'm going to bring, gosh, I need to move again. I'm writing too big. So then 9 equals x squared because x squared comes over and multiplies. So then 0 is x squared minus 9. Now, I'm going to give you a second to recognize this special pattern. Hopefully you recognize that it's DOPS. All right, so it's something squared minus something squared. So this is x minus 3, x plus 3, which means the answer is 3 and -3. So what this means, if I zoom out for a second, I can't zoom out far enough really, but this is saying that the coordinates of the turning point are 3 and -3. This was a cubic graph. If I go back up to the top, oh, okay, that's not very helpful. There are 2 turning points. Okay, sorry, it's not a cubic graph. I forgot what shape we had. What we're saying is that these are the coordinates, or these are the x coordinates of the 2 turning points. So if x is 3 and -3, I want to find, so let's just go back up here, x is positive and -3. So I need to put these solutions back into the original equation to get my y coordinate. Remember, the x solutions are the coordinates of turning points. It's where the derivative or the gradient is 0. So I have 3 squared plus 9 over 3. So 9 plus 9 is 18 over 3 is 6. So that means the first coordinate is 3, 6. The second one is going to be -3 squared plus 9 all over -3. The top is exactly the same. This is 9 plus 9 is 18. But this time we divide by -3. So we've got -3, -6. So these are the coordinates of my 2 turning points. Great. I still don't know if they're maximums or minimums. So what I'm going to do is go down here and I'm going to write them in a different color just so I can keep track of what I'm doing. So I've got 3 and 6, and I've got -3 and -6. I would like to know if these are maximum or minimum turning points. So I am going to use my second derivative. So let's go back to what we said the derivative was. So that means that why did it, oh geez, I clicked the thing again. Don't click that. Undo, undo. Zoom out, zoom out. Okay, sorry. All right. My second derivative, don't touch the button again. Oops, looking weird. All right, so I need to derive the first term, or actually, first of all, let's rewrite it. So 9x to the -2. All right, I should have used the top one, shouldn't I? Okay, so let's do this. Now I need to find the second derivative, so I shouldn't have said that at all. Okay, Anyway, you get my point. The second derivative is now, this disappears, and then -2 times -9 is +18, and then I subtract 1. All right, so my second derivative is 18 over x cubed. So what I'm going to do now is put those values, so the -3, I've got -3 and +3. I'm going to put these values into my second derivative, and actually, let's just do it first and then I'll tell you. So 18 over 3 squared, cubed, and 18 over -3 cubed. So this is 18 over 27, and this is 18 over -27. All right, so this is greater than 0. This is less than 0. So I've got two different solutions. What that means is if a second derivative is greater than 0, which this one is, that makes it a minimum turning point. It's kind of the opposite to what you think. So greater than 0 makes it a minimum. Less than 0 makes it a maximum. So that's the usefulness of a second derivative. It tells us the type of stationary point we're looking at. Okay, so that is just way too much stuff, and I probably should have written it better. All right, let me save that. Let's do another example. Now that you understand the kind of thing I'm talking about, let's try it again. All right.